The broadcast is now starting. All attendees are in listen-only mode.
Good day, everyone, and welcome to the April PNW DEWS Drought and Climate Outlook webinar. My name is Holly Prendeville, and I'm the coordinator for the USDA Northwest Climate Hub. This bi-monthly webinar series is hosted by NIDIS, the USDA Northwest Climate Hub, and the Oregon Climate Change Research Institute. It's designed to provide partners and other interested parties in the Northwest with timely drought and climate information. Each webinar is tailored to reflect recent, current, and forecasted conditions and climatic events, but will also include discussions of observed impacts and other relevant updates from across the region. Webinars and recordings and other supporting material are posted on drought.gov later this week. Note, after today's webinar, you'll have an opportunity to provide us feedback to help us improve this webinar series. So we would appreciate it if you would take a moment to let us know what you think. Next slide, please. Today's speakers include Zach Hoylman from Montana Climate Office, who will give us a presentation on climate recap and current conditions. Then we'll hear from Henry Pye from the National Weather Service Northwest River Forecast Center, giving us a presentation on seasonal conditions and climate outlook. Then we'll hear a joint presentation from Kim Hall with the Nature Conservancy and Ann Schwind with Montana Department of Natural Resources, who will provide us with a new tool and land manager's perspective, linking drought drivers to response strategies, a Montana application of the EcoDIVA tool. There will be a question and answer box at the right side of your slide. So as the presentations are going, you're welcome to put your questions in there, and then we'll get to a question and answer period after all 4 presentations. Before we begin the presentations, I want to highlight the partners who make this webinar series possible. The Northwest Climate Hub develops and delivers science-based, region-specific technologies and information that will assist agricultural and natural resource managers with climate-informed decision-making in Idaho, Washington, Oregon, and Alaska. Next slide. The Oregon Climate Change Research Institute, or OCRI, is a network of dozens of researchers at Oregon's public universities that work closely with other public and private entities. OCRI is housed at Oregon State University and advances understanding of regional climate, impacts, and adaptation, and cultivates climate-informed communities. Next slide, please. NIDIS, the National Integrated Drought Information System, was established in 2006 by public law with a mission to improve the nation's capacity to proactively manage drought-related risks by providing those affected with the best available information and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. NIDIS is building the foundation of a national drought early warning system through the development of regional DEWS, where networks of partners share information and actions that help communities cope with drought. While the ultimate goal is a national early warning system, we recognize the impacts of early warning information differ across the regions. Each DEWS has many of the same basic ingredients, but ultimately have their own flavor to reflect the needs of their region. The PNW DEWS was officially launched in February 2016, and their strategic plan and information on current activities is available on drought.gov. Next slide, please. To facilitate our early warning system, more precipitation observations are needed. We encourage you to join COCORAS, the Community Collaborative Rain, Hail, and Snow Network. This is a unique nonprofit community-based network of volunteers of all ages and backgrounds working together to measure and map precipitation, as well as condition reporting. Observations by COCORAS observers of precipitation events and the lack of precipitation are important to capture and improve our understanding of weather. To become a volunteer or learn more about COCORAS, go to their website, which we'll add to the chat box, or contact your state coordinator, which will also put their emails in the chat box. Next slide, please. Giving you a few highlights from the PNW DEWS region, the Bureau of Indian Affairs Tribal Climate Change Resilience Program in 2022 has announced their annual funding solicitation and that it's now open. There'll be about $46 million of funding available through the infrastructure law and annual appropriations. There'll be a webinar that will be happening here shortly, but it'll also be recorded. And then there'll be the applications must be submitted no later than 8 p.m. Alaska Daylight Savings Time or midnight Eastern Standard Time on the 6th of July. Next slide, please. Also, we'd like to share EPA's Creating Resilience Water Utilities Initiative. It's providing a series of free webinars for the Northwest in April and May for the water sector utility owners and operators, as well as other water sector stakeholders. The webinars will focus on identification and implementation of climate change adaptation options, applying for specific funding for its resilience and adaptation projects, and training overviews and details on the 5 climate resilience evaluation awareness tool modules. I'll add a link here to the chat as well. With that, we'll go to our first presenter, Zach Hoylman, who will give us a recap.
Great, thank you everyone. My name is Zach Hoylman and I am from the Montana Climate Office at the University of Montana. And I'm really excited to be here today to present the climate and drought recap for the Pacific Northwest. Drought has been a persistent feature of this landscape for well over a year now. And while it's been unseasonably cold the last several weeks and portions of the area have received decent precipitation in the short term, long-term precipitation deficits across large portions of the area continue to drive drought conditions. My presentation today will focus on how conditions we've experienced in the last couple of months compared to the historical conditions. Specifically, I'll focus on precipitation and temperature conditions over the last water year, the last 60 days, 30 days, and I'll be looking at snowpack, soil moisture, and streamflow conditions and how these conditions have contributed to drought conditions across the region. I'm going to attempt to complete all of this in the next 12 minutes and then hand it off to Henry for a discussion of our seasonal outlook. So let's start by taking a look at temperature and precipitation anomalies for the water year so far. The current water year is the period extending from last October to a few days ago, April 20th. In the figures, conditions from October 2021 to present are compared to those for the same time periods between our reference period for this analysis, which is 1981 to 2010. The figure on the left shows anomalies in temperatures using GridMet data from the Climate Toolbox. Anomalously warm temperatures are indicated by red shading, normal conditions are represented by white shading, and cooler conditions are represented by blue shading. Generally, temperatures in western Montana and eastern Idaho, along with the majority of Oregon, are warmer than normal. These range from about ½ degree Fahrenheit above normal to upwards of 2 degrees in portions of central Oregon, western Montana, and eastern Idaho. Temperatures along the coast of Washington, in eastern Washington, and southwest eastern Idaho are well below normal. To put this into historical perspective, let's look at the temperature rankings for the last 127 years from NOAA's National Climate Data Center for October through March. Montana had the 17th warmest conditions on record, while Idaho reported the 18th warmest. Oregon reported the 14th warmest conditions on record. Washington experienced more normal conditions, reporting about the 37th warmest conditions on record. The figure on the right shows water year precipitation anomalies, where wet areas are indicated by blue shading, normal precipitation amounts are represented by white shading, and dry conditions are represented by brown shading. The majority of Oregon has experienced below normal water year precipitation, ranging from about 50 to 90% of normal. This dry trend extends into north central Washington and western Idaho. West central Montana received slightly below average precipitation as well over the water year to date. Looking further north, portions of northwestern Washington and northwestern Montana have experienced normal to above normal precipitation. In terms of precipitation rankings, this has been Montana's 41st driest year, Idaho's 38th driest year, Oregon's 26th driest, and Washington is relatively normal with its 84th driest year on record. So now let's move to what we've experienced over the last several months, specifically from the 20th of February to the 20th of April, or about the last 60 days. In this slide, on the left, I've shown temperature departure from mean over the last 60 days. White to blue shading represents cooler than normal conditions, while red shading indicates warmer than normal conditions. As you can see, the entire domain has experienced below average temperatures during this time period, ranging from about ½ degree Fahrenheit to 5 degrees below normal. The only exception to this generality is a small portion of southern Oregon, which experienced relatively normal conditions. Overall, temperatures have been relatively cold for this time of year. The figure to the right shows our anomalies in precipitation over the last 60 days. Increasingly brown areas represent below normal precipitation, white areas represent normal precipitation, and green areas represent locations with above normal precipitation. I'll call your attention to the area of brown extending from Oregon to Idaho and extending up into southwest Montana. Here, precipitation has been well below normal, with only about 25 to 70% of normal falling in the last 60 days. Portions of north central Washington also experienced similar deficits in precipitation. On the other hand, western Washington and western Oregon, along with the central border of Washington and Oregon, experienced wetter than normal conditions, with values ranging from about 110 to 150% of normal precipitation. Portions of western Montana also experienced wetter than normal conditions of the last 60 days. As we transition to the last 30 days, we see similar conditions and patterns across the domain. Once again, on the left, temperatures have been generally about 2 to 4 degrees cooler than average for the majority of the region. Again, with the exception of south central Oregon, which experienced slightly above average temperatures. Precipitation deficits over the last 30 days shown on the right also show similar patterns to those at 60 days. Similar to before, eastern Oregon, Idaho, Montana, and northwestern Washington all report below average precipitation. In contrast, the central border of Oregon and Washington experienced well above average precipitation in the last 30 days. Similarly, western Oregon and western Washington, along with central Washington, also experienced above average precipitation. And as a quick note, you too can track these conditions and how they're progressing throughout the season by going to the climate toolbar link that I put at the bottom left-hand side of this slide. Now let's talk a little bit about where we stand in terms of snowpack conditions for this spring. On the left, I've shown the percent of average snow water equivalent, or SWE, for April 21st across the mountainous areas in the Pacific Northwest. These data are measured using snow pillows at snowtel sites across the Rocky Mountains and Cascades. You can think of snow water equivalent as the amount of water that would exist as a depth if you were to melt the entire snowpack at any given point. On the right, I'm showing a slightly different estimate of SWE anomalies calculated using a snow model maintained by NOAA called SNODAS. Let's start by looking at the SNOTEL data. The left-hand figure shows average snow water equivalent for each of the hydrologic unit code, or HUC 6 watersheds. Red and orange shading indicates below normal snowpack conditions, green indicates normal conditions, and blue indicates above normal conditions. And as a note, this color scaling applies to both figures here. But again, starting on the left, as you can see, basins in western Montana, northern Idaho, Washington, and northern Oregon are generally between 100 to 120% of the 30-year average for this time of year. Unfortunately, SWE, or snow water equivalent, is generally below average in southern Oregon and southern Idaho. Let's shift to the right-hand figure now and look at the SNODAS dataset. The SNODAS model takes an assimilation approach to estimating snowpack dynamics, leveraging both a snowpack model as well as observations such as SNOTEL data to make its estimates. The main difference here compared to SNOTEL is that SNODAS estimates snowpack across the entire domain from low to high elevations. Here we see a similar story to SNOTEL, where snowpack is generally at or above normal at high elevations, but it is below average in many of the low elevation portions of the domains. This is especially apparent in western Montana at the headwaters of the Clark Fork and Flathead Rivers, major tributaries to the Columbia. The persistent drought conditions continuing from last year, in conjunction with the lack of significantly above average precipitation in the short term, have set the stage for dry soil moisture conditions across the Pacific Northwest. Soil moisture is a key storage of water for natural and agricultural vegetation, and springtime is a key time for recharging this important reservoir. In this slide, I've shown the Climate Prediction Center's modeled soil moisture percentiles for April 21st on the left, and soil moisture anomalies from NASA's Soil Moisture Active Passive, or SMAP mission, on the right. Starting with the left, red colors represent below average conditions, while green colors represent above average conditions. As you can see, soil moisture is generally below average in the eastern portions of the domain, with wetter than average conditions along the northern Washington coast. Particularly strong deficits, or areas without much soil moisture are shown in southern Oregon and southwestern Montana. Shifting to the right, the SMAP-based soil moisture estimates are generally more optimistic than the CPC's model estimates, though similar patterns exist. Southern Oregon and eastern Washington show well below average soil moisture conditions, along with portions of southern Idaho. Looking directly at current streamflow conditions now, here's a map of the USGS stream gauges and flow rankings across the Pacific Northwest for the last 28 days. Across the gauge network, blue symbols indicate greater than 90th percentile flows for the same time period, or well above average stream flow. Light blue is between the 75th and 95th, so also above average. Green is the 25th to 75th percentiles, or average. Orange is the 10th to 25th percentiles, or below average, and red is the below the 10th percentile, or well below average. Generally, the majority of gauges across Washington, northern Idaho, and western Montana are recording normal to above normal stream flow, with a few exceptions. However, stream flow along the Oregon Cascades and southern Idaho are showing well below average flow. As the spring season progresses, it will be important to track the melt of mountain snowpack and see how this affects seasonal stream flows. A slow melt with plenty of time for snowpack water to percolate and recharge soil water and groundwater reservoirs will be important to avoid further intensification of drought conditions across the Pacific Northwest. Speaking of drought, let's sum up all these observations by looking at last week's Drought Monitor drawn up by Brad Rippey at the USDA. As you can see, drought conditions continues to be persistent across the Pacific Northwest, despite cooler than average conditions over the last several weeks. Low stream flow, dry soils, and precipitation deficits over the last 3 to 12 months, and even longer, have produced wide regions of exceptional, or D4, and extreme, or D3 drought conditions in Oregon. In Washington, a sliver of extreme drought exists, along with central portions of the state. Fortunately, recent precipitation over the last several weeks have alleviated drought conditions in northwest Montana. Conversely, drought has been intensifying across most of Idaho over the last several weeks, especially in central Idaho. And with that, I'd like to summarize some of my analysis here by talking about temperatures. Generally, it's been warmer than normal this water year in Montana, and across the Pacific Northwest, but the last 60 days have been well below normal across the entire domain. Precipitation, water year precipitation has generally been drier than normal in Oregon and many other portions of the domain, but in the last 30 to 60 days, the majority of the region has seen below average precipitation, especially in Idaho, western Montana, eastern Oregon, and northeast Washington. These conditions and long-term deficits have contributed to further reductions in soil moisture, low stream flows, especially in the Oregon Cascades and in southern Idaho, and stable drought conditions, especially severe and exceptional, have persisted for many months and are likely to continue unless significant moisture comes this spring. With that, I'd like to say thank you and hand the presentation over to Henry.
Thank you very much, Zach. Next, we'll hear from Henry Pye with the National Weather Service Northwest River Forecast Center to hear an outlook.
All right, hopefully y'all could see my screen, and I've hopefully unmuted myself. So thanks for the introduction. My name's Henry. I work at the Northwest River Forecast Center, and our office is stationed at Portland, Oregon. Let's see here. And so just quickly, some take-home messages up front here. I just wanted to talk about a little bit about multi-year precipitation, which we've touched on earlier a little bit, at least for this water year. But I just wanted to highlight that our southern domain shows persistent dry conditions for essentially the past couple water years. And then how that relates to water supply forecasts, which is what our office does quite a bit of for the April through September timeframe. And so the main highlights here are it's near normal for much of the northern part of our domain, which we've kind of hinted at before, and it's below normal for much of our southern portion of our domain. And when we sum this all up at the Columbia River at the DEWS, it is slightly below normal. And looking further out in terms of longer term outlooks, we have higher probability of lower precipitation and higher temperatures. Now, looking here at some water year accumulated precipitation. So on the left-hand side is the prior water year's seasonal precipitation, and on the right-hand side is the water year to date, which I don't want to cover too much and take luster from what Zach was just talking about. So our color scales are a little bit different here. So blue is, again, hopefully intuitively wetter than normal. Light green here is near normal, and red here is well below normal precipitation, or drier than normal conditions. And so what we have here are some strange polygons. They are our watershed boundaries for our forecast locations that we give both water supply forecasts for. And so what we just wanted to highlight here on both the left and the right-hand side are the persistent, like orange and red colors that we see, both in Southwest Oregon, Central and Eastern Oregon, and then Central and Southern Idaho. And so those are the areas I'll probably be touching on most significantly in this presentation. Now, discretizing a little bit in terms of monthly temperature and precipitation, we did talk about 60-day relative to normal in our prior presentation, but this is segmenting them into a monthly time scale. So our top row is a temperature departure from normal. Our bottom row is a precipitation percent of normal. And this left-hand column with the spatial figures has the month of March, and on the right-hand side is the month of April to date. And so on the left-hand side, starting with the temperature departure for March, it is showing warmer than normal conditions for the central portion of our basin. And then again, for the month of March, much drier than normal conditions for across our basin. And then contrasting that with April, where we have so far seen much well below normal conditions for temperature, and then actually a bump up in precip for this month so far. Now, how does that look in terms of current snowpack and observed streamflow? And this I'll touch on very lightly here. What we see in terms of snowpack is actually well above normal conditions, but I wanted to highlight that in the southern part of our domain, a lot of times peak SWE is considered for April 1st as a period of peak SWE. So even though some areas in Oregon show some really high percentages, they actually should be depleting this time of year. So sometimes those percents of normal can be kind of deceiving. And I did want to highlight the color scale is essentially what is similar as our precipitation color scale with a few more buckets. And we do have these white dots here that indicate that snow tail gauge is melted out. And again, I also want to highlight here that our Canadian snowpack is well above normal, and that actually provides quite a bit of our water supply forecast that we discuss later on. And those snow pillow data are provided by BC Hydro. And then moving on to the right-hand side is our observed streamflow, kind of our forecast locations. And so each icon is either a USGS gauge or a partner gauge that we help forecast for our locations. And this is the color scale is similar to actually exactly the same as our snowpack on the left-hand side. So on the right-hand side, the observed streamflow, it kind of differs from the snowpack conditions because this is the accumulated stream flow for the whole water year in terms of a volume. So not just the 28-day stream flow conditions that we looked at before. And so this map kind of very closely mimics essentially the water year accumulated precip to date on the right-hand side. So essentially most of our domain for observed stream flow is pretty deficient, essentially in southern Oregon, especially once we get onto the east of the Cascade Range, and then again in the south and central Idaho. And then again, it creeps up a little bit into the eastern Washington domain, but just keep in mind as the further you go up north, the more snowpack dominated it is, and those colder conditions in April actually have kind of dampened at least some of the potential melt that should be occurring at this time of year. Now, looking a little bit out into the future here, we have our precipitation forecast here for the next 10 days. On the left-hand side is accumulated precipitation. And so anything in red essentially is showing essentially 2 inches or higher accumulated over the 10-day range. And so there actually isn't a lot in that two inches or above. It's mostly concentrated in the Cascades and some in the Olympics. But whenever we contrast that with climatology on the right-hand side, we see that most of the map on the right-hand side is dominated by the yellow, orange, and red colors. And so those are meaning that it's drier than normal, essentially. So that is essentially the coastal range is showing probably the biggest deviations from normal. Now, when we take all that, we take the observed data, the snowpack, and then our forecasted precipitation, and then beyond the 10 days, we apply the applied climatology or the climatology for precipitation and temperature to generate forecasts for April through September. And so what I have plotted here are a couple different flavors of our April through September forecasts. So on the left-hand side are our April through September forecast represented at percents of normal. And on the right-hand side, we have them presented in terms of driest ranking, essentially. So just keep in mind that we're a month into April. So, you know, a part of our forecast is including roughly a month of observed data already. And so essentially what we see on the left-hand side is a pretty good mimicked plot of what we had in terms of observed stream flow so far. So there are deficiencies again in southern Oregon, especially east of the Cascades. And then again, a lot of deficiencies in central and southern Idaho. And it is creeping up in Washington a little bit, but maybe a little bit less so than we saw in that observed stream flow, because there's still quite a bit of snowpack in some of those mountain ranges. And now when we look in terms of the streamflow rankings on the right-hand side, in terms of the driest rankings, what we're really looking for are the dark red dots here, essentially. So that is the driest 10-year or driest 10% period, and we have a historical record since 1949. And so what we have here, that dark red areas are kind of in the headwaters of the Rogue in Southwest Oregon. And then we have a few spots in essentially, or several spots actually in central and eastern Oregon. And then we have several spots in southern and central Idaho. Now, expanding a little bit, this is going to be a pretty busy plot, so hopefully I'll try to walk you through it here. So first I'll start out on the right-hand side with this big evolution plot. So the x-axis starts at the beginning of the water year, and then each one of those box plots represents one of those April through September water supply forecasts. The y-axis here is the seasonal volume in million acre feet. And so just telling you right now, essentially we make water supply forecasts every day. And so each one of those box plots represents that forecast. And then the inner quartile range is represented by the yellow box, and the 10 and 90% exceedance values are represented by the whiskers. And the horizontal kind of magenta bar there is the 50% exceedance. And then behind the plots a little bit, you see this green horizontal line, that is the 30-year normal. And that's been updated recently to represent the 1991 to 2020 normal. And so I just kind of want to talk you through here. So if you recall that the last water year was pretty dry, so our first forecast in the water year back in October actually began below normal, below that green line. So our 50% exceedance began below that. We did pick up essentially where in January we were actually looking pretty good, near or above normal. But things had dried out considerably since January, with leveling off since April. But just keep in mind, I believe Andy showed this last time we presented, that you know, April and beyond are generally the drier parts of the year. So even though we may have gotten above normal precipitation, we're going to need quite a bit to pull us back to that normal green line. And so going to the table a little bit, I won't try to talk to you too much about it. You just kind of see the April through September highlighted in the far left column. Those gray columns in the middle of the tables are the 50% exceedance. So they represent kind of those horizontal bars that we were looking at before, but they actually give the volumes, numeric volume in there, and the percentage of normal that's associated with that. And then the table columns to the left and right of them represent the whiskers, and then the 30-year average, that green line, is given as well, just absolute values in terms of 1,000 acre feet. And so you could, if you go to that URL in the bottom right, you could actually highlight different forecast periods, and that'll populate different plots on the right-hand side. And you could also highlight a couple of different other water supply products, which I won't go into detail here, but you could feel free to ask questions in the chat. And so whenever we want to split out that seasonal forecast and look at individual monthly forecasts, we can click on some of the link below. There are other links on our website that will bring you to it from that prior slide. But again, I just want to highlight that our forecasts are typically the box plots. We added the min and the max values as the yellow dots. And then further back you go in time is the blue bars representing the observed monthly stream flow volume. And then again, the x-axis is water year, the y-axis is volume, and those green dots are the observed, the 30-year normal for observed stream flow for this gauge. And this is, I forgot to mention, this is a gauge for the Snake at Lower Granite Dam. So this is a big contribution or aggregate location for a lot of the Snake River, and that flows from essentially south and central Idaho and parts of eastern Oregon. And so just wanted to highlight here, again, since this is in the southern portion of our domain, and we kind of know that there's deficits that have been seen for the past couple of years, that the dynamics for this water year haven't really changed. Our forecasts are all well below normal, essentially from April through July. August and September, we're not anticipating that much stream flow runoff. And then just in general, I wanted to highlight the dynamics between March and April. And so if you remember that March, we saw warmer than normal conditions and then drier, less precip as well. And so that actually led to enhanced snowmelt. So that actually bumped stream flow closer to normal, while the actual temperature, cooler than normal temperatures, have caused a lot less runoff, which has caused this April runoff to be a lot less than normal. So that were some of the major highlights here, other than just mentioning that, yeah, the Snake River is pretty well below normal for the most part. And now I just want to quickly touch on the Oceanic Niño Index. So just realize the period highlighted in the red box was for October, November, and December. And so that forecast is kind of used as a slight correlation for future forecasts. The forecast for this year is represented again by the box plot. And if you could kind of see a little to the bottom, kind of left and lower is 2021. So the past couple of years have both been forecasted as La Nina conditions, but are well below that correlation line. But just keep in mind, we do not include this in our stream flow forecast that I've been presenting so far. And now looking at the 3-month outlook, and this is provided by the Climate Prediction Center. So on the left-hand side is the seasonal temperature outlook. And so essentially anything in the red is showing higher probability of above normal temperatures. And so essentially higher probability of warmer conditions. And so that's shown essentially most of our domain other than west of the Cascades. And on the right-hand side is the 3-month outlook for the seasonal precip. And so that is showing a higher probability of below normal precipitation for essentially all of our domain. And so that's definitely concerning for drought conditions. And now looking at, again, at the Climate Prediction Center's seasonal drought outlook, what we see here is that we have a lot of brown for much of the Pacific Northwest and some yellow kind of in that Idaho and Montana, Idaho Panhandle and northwest Montana. And the brown represents drought is persisting, and the yellow is showing that development is likely. And this has changed a little bit since essentially a couple months ago. So the brown was not present in that eastern Washington area before, and then that yellow area is also new for this map that was made, I believe, within the last week. So finally, here's a plug for Northwest River Forecast Center's last water supply brief that's in the books, and you can find more information online. And I just wanted to just kind of highlight the take-home messages. I won't try to reread everything for y'all. And I just wanted to highlight a quick note on stream flow normals, if I have time. This was, like I mentioned before, we did update our normals from the 1991 to 2020. And this is just showing the difference between our prior normals that were 1981 to 2010. So anything in red essentially showing a change lower in the normals there. So I believe that was all the slides I wanted to present. I will actually hand that. stop presenting here.
Thank you very much, Henry.
Yeah.
Next, we will hear from Kim Hall with the Nature Conservancy and Ann Schwinn from Montana Department of Natural Resources about their application of EcoDIVA.
Thank you very much. Can you hear me?
Yes.
Great. Yep, so it was just said, my name is Kim Hall. I'm with the Nature Conservancy. I'm actually based in Lansing, Michigan. And my partner today is Ann Schwinn from the Montana Department of Natural Resources and Conservation. And our title is Linking Drought Drivers to Response Strategies, a Montana application of the EcoDIVA tool. And as you can guess from that title, we're going to be talking more about helping resource managers and policymakers understand what to do when they get forecasts like the ones you've just seen, and trying to kind of put all of the information that can be available about both current drought patterns and also climate change projections into a context that supports proactive resource management. And I just want to take a second to acknowledge that the work that I'm going to be talking about today builds from a long-term collaboration that came about through a SNAP Ecological Drought Working Group, and you can Google that to find out more about what we did. And I also would like to acknowledge my co-PIs on this project. They are Shelley Crosby, who led the terrestrial ecosystem modeling. She's from Conservation Science Partners. Molly Cross from the Wildlife Conservation Society. She and I both work together on climate change adaptation and outreach with stakeholders and kind of science communication. And Jason Dunham, who is with USGS, and he leads the freshwater components of our modeling, which I'm not actually going to talk about today, but hopefully we'll get to talk to you about sometime soon in the future. And I want to acknowledge our funding. We're funded through NIDIS's Coping with Drought program. We're part of the 2020 Ecological Drought cohort. There we go. So as I sort of hinted at a second ago, the intent of our project is to really help managers and policymakers address the changing impacts of drought on ecosystems. So specifically, thinking about how do climate change and human land and water use interact with the meteorological variables that you've just seen to influence how much water is available for natural systems, and thinking both about impacts to biodiversity and also to all of the ecosystem services that our forests and wetlands and streams provide that support local communities. Our goal is to support anticipatory management responses in ways that recognize the existing knowledge of our managers and policymakers, and also sort of help with constraints in sharing information across jurisdictional boundaries, for example. We are developing a tool that we call EcoDIVA. That stands for Ecological Drought Impacts and Vulnerability Assessment. I'm not actually going to give you a link to a tool right now because it ends up we're in the middle of updating it with the data that I'll show you today, but I'll be happy to share that out so you guys can take a look at it soon. The idea here behind EcoDIVA is to deploy our EcoDrought framework that I'll show you in a second, and a visualization tool that uses data from a retrospective modeling process that helps us link drought impacts on focal ecosystems to adaptation strategies. So trying to basically show what the key drivers are so we can tie those to adaptation strategies and hopefully do something to reduce the impacts. We have 3 case study project areas. One is in the Upper Missouri Headwaters region, where Ann is our queen of knowing everything about the system and helping us figure out how we can communicate information with the folks she works with. And then we're also working under the current grant in the Flathead River and also in the Harney River Basin of Oregon, so Southeast Oregon. These different applications incorporate different ecological systems, and the newer ones that we're working on now have a much stronger component of human water use than the one that I'm about to show you. Okay. So I mentioned that Molly and I both focus on climate change adaptation, and our framework for understanding ecological drought is really strongly tied to climate change vulnerability assessment approaches. When we think about how to connect changes in drought risk to focal ecological targets, we're basically thinking about it using the same framework that one would use if you were looking at climate change vulnerability more broadly. We start out by thinking about exposure to drought factors and then connect those to the sensitivity of ecological systems and the potential for adaptation. And that potential for adaptation can be inherent to the ecological systems themselves, or they could be something related to the management system. Another really important aspect of the way we have framed ecological drought in this project is that we are really interested in fully accounting for the effects of people in the landscape in terms of both the effect they have in changing the availability of water for ecological systems, either through direct water use or through how the land is managed and how that management influences where water goes on the landscape. And also in thinking about what people can do to kind of feed back into the system in a positive way. So how can we change management to reduce ecological drought risks to the systems that we care about, that protects, again, both biodiversity and the ecosystem services that people depend on. So this is our basically the structure of our framework. Again, aligned at the top row, those are our climate change exposure factors, both the meteorological factors, amount of rain and snow, and also considering the effect of anthropogenic climate change. So droughts occurring under hotter conditions, so you get higher evaporation and basically thirstier air in terms of how those droughts emerge across the landscape. And then thinking about the factors that influence the sensitivity and ability of those systems to adapt. So what are the landscape characteristics that underlie the focal systems? Those can really influence where water goes and how available it is. Things like tree species under ecological characteristics can influence how sensitive a species is to a particular drought event. Some species are more drought tolerant than others. And then thinking again about the human components, the human land and water use, our streams being diverted to help irrigate pastures, for example, or our streams being dammed for other purposes. What are the effects also of natural resource management? So how are those forests managed, and how is that influencing, for example, the stocking density of trees and competition between trees that can again increase sensitivity? How can we think about all of those pieces together and make some changes that will reduce risks to both nature and people? And one thing again I want to highlight is the idea is we're really trying to help people think both about how to use all of the information, like the information you just saw, to make decisions now, but also to think about how to plan for future risks in kind of a bed hedging way, knowing that it's always going to be hard to know what's going to happen a year or 2 years or 5 years from now. And trees live a really long time, so you want to be thinking about multiple time frames when you think about reducing drought risks. So I mentioned that we use a modeling approach, retrospective modeling, and the dates that are in our retrospective model for the Upper Missouri headwaters, which is shown in that map in the upper left, focused around the 2001 to 2006 drought that's shown in that image in the bottom from the Drought Monitor. And this image on the upper right just gives you a sense of the topographic variation within this set of 8 watersheds that are our focal unit in the Upper Missouri headwaters. So each of these watersheds was in the process of doing a water planning effort that Anne will talk about. And so we manage, all of our models are basically at the unit of those individual watersheds to help inform those efforts, those planning efforts. So this is our response variable. Our ecological response is the greenness of forest canopy cover. And so here again in green are trees that actually did okay through that 5 or 6 year drought period. So their greenness didn't really change much. The red ones, on the other hand, are ones that showed a decline in greenness. And what we're trying to understand here is that what are the factors within this landscape in terms of both, the topography and the tree density and the tree type and the exposure to all those different precipitation variables that help us understand why some of those trees did okay and some of those trees did much less well. And we don't actually know that these trees necessarily died based on this, but we know that their trend was not as good as it was for the ones that stayed green. And for those that were interested in the overall modeling approach, we used a machine learning approach called boosted regression trees, and I'd be happy to follow up with anyone that would like to know more about that. Returning back to the ecological drought framework, these are the pieces that we're actually able to represent in this first model. We've got the meteorological, the landscape, the ecological, and some climate change pieces. And in the future ones that we're working on now, we've got more examples that include human land and water use and more management data. But just to give you a little bit of a sense of what this looks like, these are a couple of the ecological variables that are in the model. You see that these are tree types. So again, an aspect of sensitivity. We've also got a canopy cover layer. So this is basically the density of trees in those different areas. A third ecological variable that we have in the model is time since fire. Those other variables that are showing up there in gray are ones that we tried and ended up taking out of the model for various reasons. And again, I'd be happy to follow up with people that are interested in those details. Shifting on to a different type of variable, this is a map of the climatic water deficit, which is the difference between the actual evapotranspiration and the potential. So sort of how much more water would the plants in the system like to have that they didn't have available. And basically this is indicating that you've got higher deficits on hotter slopes. So again, this is capturing, one way of capturing the effect of the landscape in influencing where water goes and how it's available to growing trees. A couple more that we have in this component of the model include Dave Theobald's heat loading index called chili and slope. These other variables that are shown again down in gray were ones that we evaluated, but were either redundant with what we already had or were not usable for some other reason. And I've got, again, the elevation in this map again, just to remind you of what that looks like relative to the climatic water deficit. The last set, these are the ones most closely tied to what you saw in the first two presentations, are the ways we've captured meteorological drought in the model. So we have 4 different aspects of that, kind of going from least to most complicated. The first is the standardized precipitation index. Then we get into SWE, which we heard a lot about. And then 2 ecologically focused drought metrics, the evaporative demand drought index, and LARI, the landscape evaporative response index. And if you look over to the image on the right, you'll see that they both kind of take into account a couple of different aspects of the water cycle. Again, we're trying to basically throw everything into this machine learning model and see which one does the best job of helping us understand that tree response. So these are some results, again, broken out by the different watersheds that I mentioned before. And not to really be able to, take you through the details for each watershed, but the idea is that you've got a little key down in the bottom right that links to all of the different variables that we put in the model. And the size of the different petals that are shown in those individual figures that are go from A to I indicate the importance of those different variables in helping explain which trees stayed green and which trees did not during that 5-year drought period. And within this interactive visualization tool, you can click on those different pieces, and it'll show you the maps for each variable, and it'll help you basically explore how those different variables are linked to the focal response, again, the tree response. You can also, in the bottom left, compare the response to a particular variable, and I'm sorry the font is so small on this one, but that's percent canopy cover across the bottom and the drought response going up the y-axis, and you can see that, in this case, all of the watersheds had an increasing drought response as canopy cover increased. But then when you look over at the right side, canopy cover is basically at 12 o'clock in all of these models. The length of that green petal can vary quite a bit between the different watersheds, which is basically telling you that there's an interaction of varying strength between the other variables and that canopy cover variable. And this is something that we are hoping to continue now that hopefully travel restrictions are limited and all those sorts of things, working through with groups that Anne is engaged with to help understand how to respond to those pieces of information. Okay, so my last slide here. Again, our intent here is to parse out the many different potential drivers of ecological response to droughts, thinking about drought conditions, landscape characteristics, ecological characteristics, and human water use, and pair them with responses that are useful. So these are something that Molly and I would be co-leading with, again, Anne and her colleagues, to help think about how do you use the different indices that are most important in each watershed to understand what to monitor and which forecasts to pay the closest attention to. How do you use the landscape characteristics to decide which places are, the best forests to focus on for storing carbon, which ones might be the best target for reducing density to reduce drought risks. All those kinds of things are what we're hoping to be able to do with these tools. So we hope that through basically translating these different variables into usable, explorable metrics, we can support really interesting and productive conversations with our partners that help us all work together to reduce drought risks. So I'm going to hand it over to Anne, where you can get the real scoop from the local partner.
Thank you, Kim. As she said, I'm Anne Schwend, and I'm a water planner in Montana. I'm located in Helena, and I cover basically the upper Missouri basin, which runs typically from Yellowstone up to Glacier and the Canadian border. And I work with a lot of the watershed groups and the conservation districts and the locally based community organizations that are doing drought and water supply management and planning. And this whole project, just a quick background on it, in 2014, this area was selected as a demonstration area for the National Drought Resilience Partnership. And this was something that came out of the Obama White House. And the idea was to demonstrate what would it look like when all of the federal partners came together to focus on an area and deliver resources and have these conversations and begin to do proactive drought planning. So the area, as Kim said, is 8 different Huck 8 watersheds. And we were really fortunate that we have very functional groups that are already working in those regions that were, they had varying interests of wanting to begin to do drought planning. And as we launched into this, you can see some of the partners that are up here in the National Drought Resilience Partnership, but NIDIS and NDMC really helped us with kicking it off and saying, okay, how do we need to do this? Let's start this conversation, because most of these locally based coordinators were in varying levels of doing drought planning and didn't really have a good understanding of how to do that. So what we were trying to do was teach the drought coordinators how they would do that. Fast forward several years, or a couple of years, then the SNAP Ecological Drought team reached out and said, we're really interested in, we have this framework that we've developed that Kim showed a couple of times, and now how do we really link that into the conversation? Because many of you know, those of us that have been doing drought planning, typically when we talk about drought planning, it's focused on forecasting and predicting, and then we sort of jump to responding when we're in the middle of a drought. And so what we were really trying to do in the Upper Missouri was think about how can we understand all the different aspects of drought and those impacts, and looking at vulnerability assessments more comprehensively. And the ecological drought is a really tough conversation to have. People don't really, producers and water users on the ground, think about irrigation water or community water systems. They sort of think about streamflow, but they aren't really as connected to what are all the things that are changing that, or what are those factors that are coming into play that are having an impact. And especially when we have long-term drought going on, like we do in the Upper Missouri, what does that look like cumulatively over years? So you have that conversation, and we use that framework to really get people to begin to think more about ecological drought and what does that look like, and what are those impacts, and how are those impacts connected to what's going on the ground. But most importantly, we need to be able to identify adaptation strategies. So what can we do to reduce the incidence and the severity of those impacts of drought when that occurs? So the EcoDIVA tool is a great tool that we're just beginning to use, looking at that and saying, all right, so local watershed group, we'll say the Big Hole watershed, if you guys have, if you go through the vulnerability assessment and you say that stream flows are really in danger, or we've had chronic dewatering, what are the kinds of things that we can do? And they begin to develop local adaptation strategies, then we can sort of create this iterative process with this EcoDIVA tool to say, if you believe that conifer encroachment or tree species, or if your forest management is really high on your list and you feel like that's an area where you want to be focusing, you can use a tool like that to begin to ascertain, is that appropriate? Is that going to make a difference? Is that going to help us? And then identify very specific locations in the watershed where the energies might be, most effective in terms of finding ways to address that. I think that it's really important for us to have these kinds of tools and to be expanding this conversation if we're going to be doing proactive planning, because there's a whole feedback loop of, if we're not really thinking about what are those strategies and what kinds of things can we do when we aren't in crisis, in drought, but going for that long game, how do we do that? And so I have been really excited to have this partnership with the SNAP team and thinking about how do we apply, how do we use this tool to answer some of the questions and be thinking more proactively to what we're going to do and how to best apply those approaches. So I think that's it. I'm really, I'm looking at what the last slide that Kim had up, emphasizing monitoring and forecasting, predicting the locations, giving us the tool to understand how our management decisions, those natural resource management decisions, how we can be influencing that with some data and a clearer understanding of what we're going to do and potentially how that will work. And then thinking about where are those locations and what are the trade-offs? What do we need to do to really mitigate and think about our future? So that was it. Thanks, Kim. You can go back to the last slide. That was all. And that's just a shot in the beautiful Madison Valley of Odell Creek, which was a big rewatering project for trying to improve flows in the Madison River flows and our aquifer recharge. That was hugely successful. So that's all I have. Thank you.
Thank you both very much, Kim and Ann. If you have questions, please put them in the question answer pod or the chat box. We do have one question for Zach at this point. Why are the 60-day anomalies compared to the 1981 to 2010 normals?
Yeah, thank you. It's a good question. I just used some data from the Climate Toolbox, and it looks like their normals haven't been updated to the 1991 to 2020 normals, and I didn't quite before this presentation have time to compute my own, but I just did a little bit of sleuthing and comparing the different normals between the two different reference periods, that being 1981 to 2010 and 1991 to 2020, and they're very similar. And so all the spatial patterns and magnitudinal directions of those anomalies hold, and for the most part, they're very, very similar. So if I'm happy to send out some updated figures in the coming days that compare the two normals, but in general, they're about the same.
Thank you very much for that. And you can see Zach's email here if you want to reach out to him or any of our other speakers. And if you have any questions about the webinar or want to get some materials, please reach out to Britt Parker. And I'll also ask for you to mark your calendars and register for our next webinar on the 27th of June. I see we have some more questions coming in. How are the fires impacting ecological drought? And I believe that's for Kim.
Okay, I'll take a crack at it, but I'm sure Ann has some local ideas too. The way that they are in the modeling is that it's another variable that helps us understand kind of the vegetation condition So if there have been more recent fires, typically there would be less vegetation there that's competing for the same amount of water. So it's just another variable that we've been able to kind of throw into the model and see how well it works. Anne, anything to add there?
Yeah, I would say, I mean, one of the biggest issues is depending on the severity of the fire. When we have really hot burns, of course, that always follows with a lot of sediment and erosion. And then it creates kind of this feedback loop where that's changing the species composition and maybe the stream flow. It's sort of, you know, dumping a lot of sediment into our streams, changing floodplain and the hydrologic connectivity. And so it's a negative feedback loop when they are really hot, you know, extreme fires. So one of the things, an adaptation strategy is going to be forestry management, so that, you know, we're reducing some of those fuel loads. So if you do get a fire, it isn't going to be as catastrophic to the, you know, composition and to the system and what that does to the soil health and, you know, disconnecting the landscape and, you know, it goes on and on. So really hot fires are problematic.
Thank you. We are at the top of the hour, but do have 2 more questions. If folks are able to stay on, I will ask them and see what responses we get. We do have a general thank you and appreciating the case studies being very informative. And also a question, Kim, do you plan to link adaptation strategies to each of the major drivers?
Yeah, so in the prototype of the EcoDIVA tool, we basically do this in a really broad level. So we have strategies that connect to components that relate to really that same image that we showed at the very end, where it's like you've got those broad groups of things. So if you know that the shape of the landscape is a big driver, an important variable predicting your ecological response, that's really telling you that you can feel pretty confident that, you know, if you choose your location wisely, for example, again, like if you're trying to protect forest carbon in the form of trees, you'll be able to find places, cool microsites basically, where those trees are less vulnerable, and then you'll be able to find places where those trees are more vulnerable to things like fire, and also, you know, just the drought impacts that are likely to be helping make those fires hotter. So we have that in a very simple sense now, and really feel like as non-experts in terms of our team, when we first put them out there, we can kind of lay out the basic ideas, but it really takes working really closely with folks like Anne and her collaborators to say like what makes sense for this landscape. And that's really something that with COVID has been dramatically slowed down, that ability to get in a room with people and really hash out the information and link it to strategies. But that's for sure our goal.
Excellent, thank you. Just seeing time, I will suggest that you reach out to our presenters and I will share with them your questions so you all can be connected. Thank you all to our presenters and for our audience. We appreciate your time, and thank you for sharing this great information with us. I hope you all have a good day.
Thank you.
Thank you.
Thank you.
Thanks.